Hello everyone, this is Mr. 13 Things, and I'm here now today to discuss the difference between managing your points in column vectors or row vectors, and why, especially if you're going to be teaching your kids starting around 4th to 5th grade this stuff, and why you might want to get them working in column vectors so they can actually keep a visual difference in their heads between what they got to tell the teachers, what the teachers want to see, and what the engineers do or the scientists do later. Learning to have them speak to different audiences, if you would, and hopefully the curriculum will catch up in about 10 years or so. I say that unfortunately as a belief. So I'm going to put a little green here. If you remember, green is going to be our our Y direction standard. That's not me thinking it up. So I'm going to go to red here. We're learning again. Red is going to be, there's my red for later on. And then of course, if we go in the Z direction, typically it's a blue color. So I'm kind of, unfortunately, this is probably coming from those lines. I'm going to let them live there. Oh, they look kind of artistic. I'm using Camtasia to record Smooth Draw and a Wacom tablet, which I'm going to now touch on with a pen. So I am going to now talk about the difference between a row vector and a column vector. I'm going to finally lay in, of course, the black, right, which is going to look a little weird on this one. But if you notice, I've done my background not white, but not black like Sal Khan. We'll let Sal keep the black, and we'll all be a little bit off until we're as good as Sal Khan. And we'll all catch up with those 3,000 videos. So try to brand yourself a watermark, whatever else. Music, like you're seeing. But for now, we've got the colors there. And we'll talk about, in fact, now the difference between a row vector and a column vector. I'm going to do that by just kind of not colorizing right now. I'm clicking that. I now have black. So the concept, if you have a point, let's say, and your point traditionally would be something a student might say, okay, you have a point at 5, 3, an ordered pair. The student tends to know that that's 5 in the X and 3 in the Y, hopefully. They're doing ordered pair pointing. Realistically, they've been playing Game Boys for a while. They probably have known something like that. They might not realize later on that that could be a radius and an angle. But it's a two-dimensional point. And so what we want to, of course, get them to start to do is to, learn that all points are in fact 3 dimensions and write it something like this: 5, 3, know that the Z is 0, and that would be a column vector. So this would be the same point in a column vector format, right? And the column vector consists of a X magnitude, a Y magnitude, a Z magnitude, and this one here we're going to learn to carry around a lot. It is not for time, which is the most logical 4th dimension. It is just a scale factor. Well, the other way to write that vector would be to write it in a row vector, which would be 5, 3, 0, 1. But because it looks too much like this up above there, that's why we're not going to go about doing that. We're going to kind of do it the other way. And we're going to do this, of course. We're going to write it here: 5, 3, 0, and 1. So there's two reasons why we want to get our students doing this as opposed to this. It's so they can learn dual accounting, to talk to different audiences, so they can see the textbooks are going to do this for a while, but you do want to show them up at the higher levels, textbooks in linear algebra, that you do actually write things with brackets and vectors. And the last reason we're going to actually go about, or I suggest, I guess, we're not going to do anything because it's all laid out in the Core 48, is that we want to learn that they're going to take a transformation and apply it to a point. So you're going to transform the point. Just like if you have something like 5 and you multiply 6 by 5, there's lots of different ways to do that. But one way you can think about it is scaling 5 up 6 times. So this is kind of a scaling of the number 5. And so by saying that your transformation is going to be applied to the point, that's a better logical order. What I'm going to show, however, because you will run across it probably not as often as these column vectors, as you can also do the opposite here, because this is just math. So I'm going to kind of put a hard division here. So you could also do a transformation of multiplying a column vector by a matrix, a row vector by a matrix, and get the same output. So we'll do this one first, and we'll leave it at, for now, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. And it actually turns out, in some sort of odd way, this is going to look the same over there, but we're going to have to realize that there's a little bit of a difference there. So I'm going to colorize right now, do an edit undo, that if we know that this is a 4 by 4 matrix multiplied by a 4 by 1 vector, we're going to get a 4 by 1 on the output. However, if we know this is a 1 by 4 multiplied by a 4 by 4, we're going to get a 1 by 4. So this is going to yield, yes, of course, a row vector. This is going to yield a column vector. And what I'm here to prove is that these matrices are extremely similar in how they're going to be laid out, but you're going to have to really pay attention if you do want to go ahead and use row vectors as opposed to column vectors, and how you lay out this overall transformation matrix. So I'm going to colorize the translation here. I'm going to go ahead, and I think I'm correct in knowing that this is going to be also 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And we're going to let you know now that this portion are exactly the same as you go through these and compare these methods. Those are exactly the same. What's going to change, however, is your translation vector, which is a kind of a subvector within this matrix. And I'm going to go back and forth here. This is the x there, and this is the x there. Your y translation vector is there and there. And of course, logically, I hope, to learn how to run this. Your z transformation, this is basically what I'm going to show. This is a translation vector, and this is the translation vector. Otherwise, this is the rotation scale matrix. Rotation and scale. As is this. Right there, sorry, a bad arrow. Rotation and scale. So these are going to be the same, and later on you're going to see there's patterns that emerge here. But what you might want to do now is let's go ahead and now change and check the math on this on a question we know the answer to. So the question we know the answer to is going to be, I'm going to translate this, right, that point vector 5, 3, right, 0. I'm going to translate it 20 in the x, 30 in the y, and 40 in the z. Same thing over here. I'm going to translate it 30 in the x, and we'll live with that. We're going to go ahead and 30 in the y, and 40 in the z, and I want to correct that one now, so we want that to be and I will end it at that. What you may want to do is to prove that this column vector, row vector, times this transformation matrix is going to be the same, or if you want to not the same, it's going to be the transpose of this column vector transformed by this matrix here. The math will turn out to be exactly the same. One will be the transposition of the other. You should do this, and I'm now going to list the methods that are pretty easy to use, and I'll put links out emanating from this. Let's see if I can now go to my bit here. So what are the great places to do these multiplications of matrices? My personal belief, depending on where you are, Google Docs is really one of Google Spreadsheet. All right, a TI-83 calculator or any other calculator that's got any power. How about Wolfram Alpha? Or better yet, Mathematica. Now, what are not the places to do it? Probably something specialized to matrix. Get students used to using some basic tools, and this one here is allowable in a lot of exams as long as they learn how to erase the memory. I will point out that Excel does a great job of most things, and it will do matrix multiplication. However, you've got to do some chording, just like you do in the last thing I'll talk about is something called Numeric, which is an open source. Numeric, right? Which is an open source spreadsheet. So these make it a little bit harder to do matrix multiplication. Google Spreadsheet, TI-83 calculators, Wolfram Alpha make it pretty straightforward to either take a column vector describing a point and transform it by a transformation matrix, or take a row vector representing a point and multiply it by a transformation matrix, getting essentially the same answer, one being the transpose of the other. So I recommend, defy, expect, and hope that you go out and try both, but then you try to get your students or whoever you're working with, kids, to get used to this, if for no other reason, because this is basically how SketchUp keeps track of points. And if you're going to be working in 3D sooner or later, you're going to be working in Google SketchUp. Thanks for listening.